Why is gravity so weak? Why can a small magnet pull or push something away from the entire Earth? There is an idea that may explain it. But before we go there, let's explore more preliminary ideas first. The most popular quantum gravity theory of today describes all fundamental particles as vibrating strings of energy. And the theory is constructed in a whopping 9 or 10 spatial dimensions instead of the 3 that we experience in our everyday lives. But what is a dimension? A line is a familiar geometric figure and can be completely described by giving its length. It is a one-dimensional object. It can be imagined that the dimensionality of an object can be created by taking an object of one less dimensions and moving it at a right angle to that dimension. You can create a line in your imagination by thinking of taking a point and moving it. Next, consider a surface. A surface is also quite familiar. A surface has both length and width and requires 2 measurements to define it, and therefore is a 2-dimensional object. Similar to a generation of a line from a point, we can generate a 2-dimensional surface by taking a line and moving it in a direction other than the direction of the length. And a solid figure is the stuff of everyday life. It has length and width and depth, and requires 3 measurements to describe it, and is a 3-dimensional object. And like the generation of a surface from a line, we can generate a 3-dimensional object like a cube by taking a square and moving it in a direction other than the direction of the length and the width. Cylinders, cubes, and spheres are 3-dimensional objects. And now the hard part. The higher dimensions are created by moving a 3-dimensional solid in a direction other than the length, width, or height. And while that is easy to do mathematically, it is impossible for us to picture it. So let's examine how we might detect these other dimensions. We begin with bright light spreading out in a spherical shell. The intensity of the light at any one point will fall off the square of the distance from the source, because the surface that the light covers grows as the square of the distance from the source. But that is only true in 3-dimensional space. In 4-dimensional space, the light will grow dimmer as the cube of the distance. And in 5 dimensions, it will grow dimmer as the 4th power of the distance. And in 10 dimensions, it will grow dimmer as the 9th power of the distance. Now back to strings. If this membrane represents the 3 dimensions that we live in, then particles like quarks and electrons are the strings that have the endpoints forever attached to those 3 dimensions. They might look like this. But the particle that is the force carrier for gravity, the graviton, is a closed loop. It has no ends that are constrained to our 3 dimensions. So if there are other dimensions, gravity will propagate freely there as well as in our familiar 3. And that might explain why gravity seems so weak to us. We experience only a tiny fraction of gravity's true strength because so much of it is leaking out into other dimensions. But where are these dimensions hiding? One possibility, but not the only one, is that they're all around us, but incredibly tiny. If you look at a wire or a string from far enough away, it looks like a line, a one-dimensional figure. But if you get closer, or if you were a lot smaller than the thickness of the wire, then you would easily see that it has other dimensions. On the tiniest of scales, space has extra dimensions at every point. It might look something like this if we were small enough to see it. Accelerators like the LHC at CERN smash protons together at enormous energies. Perhaps enormous enough to produce gravitons. And if they do, then perhaps we might just be able to see them form in our limited three-dimensional world and slip quickly and quietly away into those hidden dimensions.